Welcome to BriscScience, the last BriscScience of the year, and for a special road trip we are out at the wonderful University of Queensland, the new Advanced Engineering Building Lecture Theatre with a lovely view of the lake there, so I hope you've all enjoyed that while you've been waiting. Thank you all very much for coming along this evening. If this is your first BriscScience, you're in for a very special treat, as we have not one but 4 speakers tonight. We'll get into that in a moment. Just a couple of bits of housekeeping. First of all, on your way in, you hopefully picked up one of the little question slips which you can use to ask questions at the end of our talk of our panellists. We'll be having a panel discussion. We do questions a little bit differently here, so if you could write down your questions as you go, at the end, the only others will come around to collect those, and we will ask as many of them as we can in the time we have. Also, if you have a smartphone, you can now take that out, set it to silent, and open up the Twitter app ready to tweet throughout today with the hashtag BriscScience. And we will be taking questions from Twitter as well, so if you have any questions there, do feel free to ask. Afterwards, as I said, we will be having a panel discussion, and then our panellists will be joining us outside for some refreshments and further discussion. So do please hang around and talk more. All right. Without any further ado, again, welcome to our BriscScience for December 2015. Tonight we are talking space. More specifically, we're going to take you on a journey from Earth to Mars and talking about where life came from and where it might go in the future. We have a fantastic array of speakers tonight who are going to cover everything from biology to rocket science. Yes, it is actually rocket science. And our first speaker tonight is somebody who you may not know by name, but you've almost certainly seen his work. He is the curator of the Sir Thomas Brisbane Planetarium and has been for, as he puts it, more than 30 revolutions around the sun. His first interest in Mars came in around 1965 when the first successful spacecraft flyby took place. And he's going to be talking tonight to us about the beliefs we've held about life on Mars and the more recent evidence and the way that we've gathered about what might be there. Could you please welcome Mark Rigby?
Thank you, Joel, and I think you can all hear me. Yes, I thought you asked me how long I'd been at the planetarium, which is 31 years coming up, but not as curator. I had a good friend. So I've been curator for 12 years, and he spent 25 years at the Brisbane Planetarium from before it was open till 2002. So I've got to at least better his record of curator. So that means I'm going to my 80s. But I often say to visitors when I'm talking about total solar eclipses, you should always try and see a total solar eclipse in your lifetime. You've got to travel usually, but there's one coming to Brisbane on Monday, 13th of July 2037, and Brisbane Planetarium is in that path, so I've got to stay till that. I've got a person just retiring who's 86 next month, so there's hope. But anyway, the planetarium, hands up who's been to the Brisbane Planetarium? Oh, very good. Okay, thank you. We did a major upgrade 2 years ago and ripped out the dome inside and everything, but there we are. We're a portal to the heavens, if you like. And so tonight I thought I'd address past allusions to modern investigations and introduce for the others who might do a bit more detail on different things. So let me make sure this is working. So we are dealing with the red planet. Hands up who's actually seen it for real in the sky. Okay, who's seen it through a telescope? Oh, good, okay. In 2003, Mars was the closest it had been in about 60,000 years, minutely, compared to some oppositions where we overtake Mars every 26 months and take it. But here we have our red planet, which has intrigued people for thousands of years. That red dot in the sky sometimes is even brighter than Jupiter. Venus is the brightest planet, but Mars can sometimes outshine Jupiter. Named for the Roman god of war, so it's got that reddish colour, and that does come from rust, iron oxidised in the soil, and an amazing planet we know now, but to ancients it was a wandering star to the Greeks, the word planet coming from the Greek for wandering star. And sometimes it used to reverse its travel, so it was an intriguing one, as the other outer planets do as well. And in this photograph, spacecraft photo, I won't go into detail, but hold on, I won't go into detail. But I thought I had my laser there. So we have ice caps on it, which were first seen after the telescope was invented, and William Herschel, who discovered Uranus in 1781, observed the ice caps there. And later on we discovered had huge canyon systems there. And I'm not quite getting the laser to work there. It's a faint one there. But huge canyon systems as well. But if I progress, the real action as far as is there life on Mars started in the 19th century, and there was a fellow, Giovanni Schiaparelli, in Italy, who in 1877, a really good opposition of Mars, so we're overtaking it, we're at a minimum distance. Not all oppositions are equal, a bit like politics. But and he drew these lines, these canali, which were mistranslated as canals rather than channels. And so canals had this sort of idea that people thought they were artificial in origin. And that intrigued a number of other people. For example, in Australia we had Walter Gale, and he's the third one on the left there. Actually, that's in Stanthorpe in September of 1922, where there was a total solar eclipse. That's the last one that came closest to Brisbane. Didn't come over Brisbane, the moon shadow, but Walter Gale was quite a respected astronomer, but actually worked in a bank in Sydney and also in Newcastle. And some of you, I'll mention it later on, but the large rover Curiosity is in a crater called Gale, and it's named for this fellow whose real profession was working in banking. But in his spare time, he was into observing Mars. He was a believer in life on Mars, an avid observer of Jupiter, Saturn, discoverer of comets. He was into establishing the British Astronomical Association New South Wales branch, so he was extremely active, associated with Sydney Observatory, and so a significant crater named for Walter Gale. So at the time, in the early 1890s, he was acknowledged as one of the world's foremost observers of the planet Mars, acknowledged by the British Astronomical Association Mars section head. So his drawings, and these are some, unfortunately I could only get very low res versions. There's some of his drawings from August of 1992. He didn't really get much attention. In fact, when Curiosity landed in the crater Gale in August of 2012, most people had probably never heard the name Gale. Because it's overwhelmed, that name, really by someone called Percival Lowell, who was a Bostonian, made a lot of money, was a diplomat, went to Japan, and he was intrigued by Schiaparelli's observations of Mars in the 1770s, 1780s. So he built an observatory with his own means on Mars Hill, as it became known later, at Flagstaff, Arizona. It's worth visiting there. He got this beautiful instrument, which I've never observed Mars with. I observed Saturn with it, but my predecessor and colleague, Jeff Ryder, who is curator, used to kid that he was Percival Lowell reincarnated. But he was there for a great opposition in '86 and observed Mars through that instrument. But Percival Lowell really was a believer in intelligent life on Mars. And in fact, there is life on the planet Mars. There's a headline. You've got to believe it. It was in the press. And so you can see some of his, one of his drawings there, and he literally made maps with hundreds of canals, melting ice from the ice caps delivered to cities, and where these canals intersected, oases, and so he was one of the main proponents of life on Mars. We now know, though, that it was all illusion. If you have, for example, a whole lot of dots and you see them at a distance, your eye will tend to blend them into a line. So unfortunately, Percival Lowell was on a dead end with, as far as what he thought was there, intelligent life on Mars. And but just as an aside, he did start the program to search for a ninth planet, which led to the discovery of Pluto in 1930. So Percival Lowell has that. In fact, his observatory photographed Pluto before he died in 1916, but he didn't realise that his observatory had actually captured Pluto. And in the same decade of the 1890s that Lowell was looking at Mars, talking about intelligent life, H.G. Wells wrote War of the Worlds, and then in Halloween of 1938, Orson Welles put that to air as Mercury Theatre of the Air. Some people that missed the beginning were really panicked, thought that we were being invaded. And you might think that's, you know, you'd have to be pretty stupid to be swayed by a radio play, but it makes me think of in the early 70s I'd turned on Four Corners late, And there was a respected ABC newsreader at the time, Ross Simons, reading stony-faced a bulletin about war had broken out between the US and China. Nuclear weapons had already been delivered onto Peking and everything, and I turned on my shortwave, I'm listening, can't hear anything. And then he says, that's what it might be like. It's then that I started shaking like a leaf when I found out it wasn't for real. So people do get sort of conned, if you like. So skip forward to 1965. I got interested in space when I was a little kid in the early 60s to mid-60s. This is my favourite mission of all missions, Mariner 4. It was a turning point, really. Even my books that I had before this mission had Martians drawn and the possibility of life on Mars, and even vegetation on Venus in some of those books I had, that I still have. But Mariner 4 was the first successful mission to the planet Mars. The Russians had tried but failed. And you can see this is, this is, you can see, I don't know if the laser there, these are the images. There are only 21 and a bit images taken, very low res, across this arc starting up here. So it showed the limb of the planet in the image 1, and you go through, by the time it got to image 11, it was just showing a totally cratered landscape. So at that point, really people thought, this is another moon, lifeless, not a possibility of life. And I remember it so well. It's, as I said, favourite mission. But it was a turning point at that stage in life, not a chance on the red planet. And that's the first image ever transmitted from the red planet. And you can see not much detail. It took over 8 hours to transmit each image, and very low resolution on those ones. But that is the first close-up. Now, you all know Carl Sagan's name at least, but you probably didn't know he'd actually got to Mars. So the Vikings were incredible. Fortunately, I was there for the launch of the first Viking to Mars, because I'd been there for the last Apollo, but, and it was about a month later. But these Vikings worked, both of them worked first time. And with the technology, Mars is a planet that really is not friendly to missions. And a lot of them failed, but the Vikings were first time. They're the only craft that have ever gone to the red planet with specific life detection instruments. And none, well, there was one where the principal investigator really still to this day believes it did detect life, but others believe it was chemical reactions. Skipping to the 80s, we have a lot of Martian meteorites on the Earth, bits of Mars that have been blasted off, and there was one found in the Allen Hills in Antarctica in 1984. And the next decade, there was this big announcement, Bill Clinton involved in it, President Clinton, and that microscopic fossilised bacteria had been found in a meteorite. So really hyped up, but it's sort of a dead end again, although some people still believe in it. Now, I'm getting to the end of my time, I'm sure. 1 minute, okay, 1 minute. We have now rovers and spectacular successes. They range from the little Sojourner, about the size of a microwave oven, to 2 of these went to Mars, Spirit and Opportunity. Opportunity still working since early 2004. It's done over 40 kilometres. And then we have Curiosity that landed in that crater Gale that I mentioned, named for Walter Gale. And that crater there was selected out of over 60 sites. And I'm going to leave it to others to really address some of these other matters. But just to show you the evidence of some of the water flow on this planet from different spacecraft. These are from the European Mars Express. And you can see that ice underneath the surface has formed a slush with the heat of the impact, and then you've got the channels running away. So it's really following the water to see if the conditions were suitable for life. And that is the crater Gale that we currently have Curiosity in at the base of an over 5 kilometre high mountain, which is really layered with it's a textbook of the history of Mars that has currently been probed. So there's lots of evidence of water. In fact, on the left is an image taken just within weeks of landing showing this, where there was this stream in that crater. Curiosity drove across it. And that is a very recent image at the base of Mount Sharp from Curiosity. So here is a world. It used to be just a point of light in the sky, but it's a whole world, a very inhospitable world that doesn't get very strong dust storms, by the way. It does get global dust storms, but not with that force. And when I was a kid, a teenager, the talk at the time of the Apollo missions was we would have humans on Mars in the mid-'80s. That was really the idea that we would have them there. Now we know it's not quite so simple. The health aspects of going there and many other aspects, and we have a speaker later about propulsion, I think, and getting there. And there are always commercial opportunities, so if it turns out that it is peopled by intelligent creatures, there's an ad from decades ago saying that they need soap. I guess on a dirty, dusty planet, cold, dry desert world, you need to clean up sometimes, and you need potatoes, for those who have seen Martian. And just to show you that we get the same sort of skies on Earth, that's the Brisbane Planetarium several years ago during a dust storm where the whole skies turned pink. So either that or we've just moved Brisbane Planetarium to the red planet. Thank you.
Thank you very much, Mark. Our next speaker is going to bring home the point that space exploration is very much a multidisciplinary venture these days. Lots of different people working together to achieve this goal. And our next speaker is a geomicrobiologist who uses both biological and geological sciences to examine the bacterial transformations of materials in the Earth's crust. And he is going to argue that we are all Martians. Could you please welcome Professor Gordon Southam?
There we are. Hello. This evening I'll talk about the idea of timing for origin of life, life in extreme environments, and then we'll kind of take an idea of a look at Mars, and something a little more controversial, this idea of are we Martian? All right, so Darwin, over 100 years ago, thought about this prebiotic chemistry, this origin of life, that we would go from inorganic materials, things like ammonia and phosphate, into organic compounds, like proteins, and from there lead on to life. Now, in terms of the timing on Earth, we've got a planet that's about 4.54 billion years old. We've got geologic evidence for liquid water by about 4.38 billion years. But we've got this late heavy bombardment where Jupiter settled into its orbit, massive amounts of incoming bolides, and this late heavy bombardment, which created much of the craters on the Moon, is thought to have potentially sterilized the planet. So we've got kind of a reset in time. Now, shortly after this, by 3.8 billion years, we've got chemical evidence for life, and this would imply that we can get life within about 200 million years. And we've got great geologic evidence for life, work done by Martin van Kronendonk at UNSW, on finding stromatolites that are 3.5 billion years old. And we know a fair bit about stromatolites living in Australia, that we have the Hamlin Pool and Shark Bay. There's still specialized, unique environments on the planet where microbes are accreting geologic material and forming these unique structures. Now, in the search for life on Mars and elsewhere in the universe, microbiologists have been focusing on life in extreme environments. And these are extreme environments from our perspective, something that isn't ambient, that doesn't have oxygen, and can be, in many cases, quite warm. We find bacteria, there's always biofilms growing in hydrothermal environments. So whether you're in New Zealand or in this case you're in Yellowstone National Park, you can find thermophilic bacteria. Now the temperature record for life in these hydrothermal vents in oceans is actually 121 degrees Celsius. Because it's under pressure, you can get beyond boiling and still have organisms growing there. From a cold perspective, and this is more important to Mars, we can find bacteria growing at minus 15 degrees C. And now water freezes at 0, but in environments like this, the pore waters within the ice and within glaciers and within permafrost becomes very salty. And in these salt environments, water stays liquid, and the bacteria can grow and divide at minus 15. This is not a great experiment for grad students because they grow very, very slowly, and it takes a long time. We've looked at acidophilic bacteria. Now, if you're working at pH 1, you would have, the rubber bib and the visor. In Yellowstone, the streams that are coming off here are full of sulfuric acid. The stitches in my boots after working in there, they just dissolved. They came apart. It was just an amazing environment. And we have bacteria growing. They're acidophiles, acidophilic, they love acid. This is how they grow. And from the salt perspective, we have halophilic bacteria that can grow in up to 700 grams per liter Epsom salts. So you can see the colors in here from the organisms that are growing in that salt. And before you think that, how harsh or extreme can salt really be, right? We've got 700 grams per liter. We're looking at about 20 times saltier than seawater. So think about that for a sec. And the student had said, do you want a sample of the biofilm there? I said, absolutely, I would. Came out of the salt looking like this. His feet almost looked like raisins, right? Because the salt is pulling the water literally out of his skin. It's certainly an extreme environment from our perspective. Now, so let's go to Mars. All right, we've got a planet today that's dry, but we've got evidence that we've seen that there's been water on Mars, and with water, this idea of finding life. Now, Viking lander. Okay, apart from the controversial experiment, dry, inhospitable. We go to Pathfinder, we got color pictures of dry and an inhospitable planet. And this idea that could life really have evolved or kind of thrived on this planet at any one time. But from the orbiter data, we've got all of these fluvial features. Okay, this idea that there had to be liquid flowing over the surface of the planet, and if we've got liquid water, then shouldn't we have life? Now, the Mars Exploration Rover Opportunity targeted Meridiana Planum, and they were targeting an iron signature, a hematite signature, that we know it can be associated with life. Go to WA, you see the banded iron formations. Okay, there's loads of hematite there. That's from a time on the Earth when we went from an anaerobic planet to an aerobic planet, and the oceans rusted out, making our iron deposits. So we were looking for something like this with respect to Opportunity. Now, when it landed and opened up its camera, this is kind of the first image that came out. It was an outcrop, and outcrops are critical to geology. If any time you see outcrops on the road on one side, you've got to look out for geologists because they'll look at the outcrop there, and they'll cross as many lanes of highway that they possibly can to show that the other outcrop is the same, and they can correlate between the two. This outcrop here, first I saw it, I thought, oh my God, this is this huge outcrop, and then the rover drove up on top of it. It was actually about this high, and the thing that's amazing, though, is being able to go on top of this outcrop. What they found is that we had sediments indicating liquid water. We've got the little nodules there of hematite, and if you're ever in WA, you can see hematite deposits on the side of the road, also indicating water. And what thrilled me is that the mineralogical data here pointed to jarosite. And I work in a lot of acid mine drainage environments, and the most spectacular I've ever seen is Rio Tinto in Spain. You've got 100 kilometers of iron oxide going right into the Mediterranean at Huelva. And these are full of bacteria, and the bacteria are fossilizing with iron. All right, so in an environment that is iron-rich, we find life, and this is pH 2, all right, and it's full of jarosite. And we've got jarosite on Mars. So if you think of the stream beds that we're finding on Mars, that it's possible that they were once similar to the Rio Tinto River in Spain. And if so, we should be able to find fossils in these kinds of environments. The artist's rendition would suggest that Mars at one time was very wet, all right, and that this type of environment should have supported these organisms. But alas, it's dried out, right? These are the kinds of images that you find on Mars today. You can look at craters, and there's lots of intriguing features. The idea that historically there was potentially these other fluvial features that were in this environment. And remarkably, as we go back over and over the planet and we rephotograph systems, we found that there's new fluvial features emerging, suggesting that while we think of Mars as being a dry planet, there may in fact be subsurface water. Evidence also from the slushy in the earlier slide. Now, this idea that there's water in the subsurface is also intriguing to the microbiologists in the crowd, because we found life in the subsurface on Earth. And this is Greg Wanger, who's a PhD student in my lab. And in the fracture that you can see that he's standing beside, we found bacteria growing okay, in the deep subsurface. This is 3.1 kilometers below the Earth's surface. So picture the tallest building in Brisbane or the observatory at the Q1. Been to the observatory? Multiply that times 12, and that's where Greg's standing. He's currently about 1,000 meters below sea level in the deep subsurface, and we find bacteria throughout this environment. Bacteria can thrive happily within fractures in rock. Now, Mars itself. So we have a planet that's smaller than Earth. Okay, and this idea of are we Martian? It's smaller than Earth. It cooled quicker than Earth. It would have had liquid water earlier than Earth. And if life could have originated on Mars during this time, when the late heavy bombardment came along, it's much easier to launch something off of Mars and enter into Earth's gravity than it is to launch something off Earth and go to Mars. Okay, so we'll have a preferential. And there are meteorites on Earth that are from Mars. So this idea that if life originated on Mars, we've done experiments where we've taken rocks, and you can see the flash on the impact in the second image there, and we've hit them with the force that could launch a rock off of the surface of Mars, and the bacteria did just fine. So we're working in the Energetic Materials and Research Testing Center. The next slide, we're firing a steel, 5mm steel projectile at 2 kilometers per second, and this was supposed to be our sterilizing impact. The count of bacteria actually increased because our little microcolonies were being pulled apart. We can launch something off the surface and the organisms will survive. Now, the meteorites that have come from Mars will have a fusion crust and that will sterilize the outside, but they don't keep to the center. Right? So we could have organisms within a meteorite where it could essentially act as a space capsule, delivering something to another planet. And when we look at fractures in rocks where we have iron oxides, we can find the iron oxide minerals and we can find it loaded with bacteria. And you can picture here that within this one clump, if this was shattered into 20 pieces, that's how we explain how the counts went up in our explosion experiment. So we can transfer bacteria theoretically from Mars to the Earth. If that happened, they would colonize Earth. It would have been a hospitable planet, right? Lots of water, great growth conditions for life. We would have produced the stromatolites that Martin has found in WA. And if this were allowed to persist and continue on Earth, ultimately we would be here ourselves. In which case, maybe he was already home. Thank you.
Thank you, Gordon. Our next speaker is a cosmologist who, when she is not investigating new fundamental physics, is normally too busy doing openings for Neil deGrasse Tyson and other famous personalities around the world. But tonight, she has kindly volunteered to come along to BriscScience to talk about not just cosmology, but astrobiology, and to ask whether life on Earth could have originated on Mars, but also more, because not all my notes are entirely up to date. Could you please welcome Professor Tamara Davis?
Thanks, Joel. Thanks very much, Joel. I was planning to talk about something like Gordon was talking about, the fact that we could possibly have been had our origins of our Earth-like life coming from Mars. But when I heard Gordon was going to talk about that, I decided to go a little bit further and look at some of the planets beyond our own solar system and find out what we can find out about those and whether they have life. Now, first, I'm really excited to be here. As Joel said, I'm usually a cosmologist, so the things that I'm looking at are usually billions of light years away. So to be looking at something local enough to have planets is really quite exciting. And ever since when I was a little kid, I wanted, I sort of had this ambition. I wanted to be the first woman on Mars. As I got a bit older, I said, stuff that. I want to be the first person on Mars. But as I got even older, I was like, well, actually, just this watching space and looking at things through telescopes is actually pretty cool, even if I don't get to go and visit. So I'm going to explain what these little wobbly things are. But first, looking for extrasolar planets, exoplanets, planets orbiting other stars. It was only in 1995 that we found the first planet orbiting another star, so just 20 years ago. Something around a pulsar had been seen a bit earlier, but this is 51 Pegasi b, or they're an artist's impression of, which was discovered using the Doppler method, which basically we looked at stars and we looked at their motion. So you couldn't see the planet, but what you could see was the star wobbling back and forth as the planet pulled it back and forth in its orbit. And so what you're looking at this little plot is how fast the star is moving as a function of time. And you can see that this has like this period that goes up and down. That's the signature of a planet orbiting it. Now, that method was the most successful way of finding exoplanets for quite some time, until this. Kepler is a space telescope, that was launched in 2009, and it revolutionized the field of exoplanet hunting. It used a method called the eclipse method, or the transit method. So here we're familiar with eclipses on Earth. This is what happens when you have the moon passing in front of the sun, for example. And what will happen is that the sun gets dimmer, fades dramatically, and then brightens again as the planet leaves. Now, did anyone here see the transit of Venus a couple of years back? That's a much less dramatic one, where you just see the little dot going across. And Venus dimmed the face of the sun briefly and made the total light that we were getting from the sun dimmer for the while that it passed in front of it. So what Kepler is doing is going and doing that with lots of other planets, lots of stars. So what happens is, as the planet goes across the surface of the star, we can't see the dot because we don't resolve anything. All we see is it gets fainter and then brighter again. And so that's the signature of a planet going around another star. If you just see it happen once, it could be anything. But if you see it happen a few times in a periodic motion, then you can be pretty sure that it's a planet. So now I'm getting to why this is relevant to life. But this is just sort of shows you sort of how many exoplanets we've known about, starting from the basically 1990s up until today. And so here, this axis says there's like 250 exoplanets is up here. So you can see that we were increasing with time the number of planets that we knew around other stars. In 2014, though, if I extend that graph up properly, you can see that it, like, really recently has just absolutely exploded with the information that we have about other planets around other stars. Pretty cool. So that was mostly due to Kepler. So here is the Kepler orrery, which is, they used to have like big little models with a planet, with the solar system and going around. This is the electronic version of that. And what this shows is not only do we know about hundreds, thousands now, planets around other stars, we actually see a whole bunch of solar systems. Here you've got the inner one. You've got multiple planets here, so you can see like there's sort of 3 planets in this system. I think this one up here even has 7. So we know not just about, and the size indicates the mass of the planet, and the orbits are just sort of the relative speeds and distances. Here's a slightly more up-to-date version, a more recent version, and then just as of like a few days ago, a new one was created as well, which also shows it sort of compared to the Earth's our solar system. And so these are actually in the correct positions. They're not really to scale, as you can imagine. The planets are a tiny bit bigger. But you can see this is sort of how big the solar system's orbits would be for compared to some of these ones that we see. So most of the planets that we're finding right now just happen to be really close to their parent star, and that's just because those are the easiest ones to find. Now, we have all of these planets, literally thousands of planets we now know of around other stars. Is there a way that we can figure out whether there's life on these? Well, one thing that we think that life is necessary for life is liquid water. So you can ask where the habitable zone of a solar system is. If you're too close to the sun, then you're like Mercury, it's frying hot, you lose your atmosphere, it's really not very hospitable to life. If you go further away, it gets too cold, you can't have liquid water, and it would be harder for life to exist. So if we're looking for life like us, you want to sort of find something that's conditions that aren't too far from Earth. And so as the planets get bigger and brighter and hotter, or the stars rather, you have to go further away from the star to be in a sort of clement zone. That's a nice ambient environment. So here's a system that's been found with a few planets in it, and this is ostentatiously one of the first ones with something that's close to an Earth-like planet, Earth-sized planet, that's close to the habitable zone. There's a couple of other possible planets in here, but they've been ruled out since this was done. But Kepler's found a whole bunch of planets in habitable zones. Here's a few of them. Another thing that you might need for life that the Earth has is a magnetosphere, something that protects the planet from the solar winds, the charged particles and stuff that are coming off the star. So if you want life, you want your planet not to be sterilized by a whole bunch of radiation. So here on Earth, we're protected to some extent by our magnetic field. So it would be cool to have one of those on a planet that we need life on as well. Now, if you can go even further and ask about where life would be possible in the galaxy. So there's a galactic habitable zone. And that's basically this sort of green radius. If you imagine this is our Milky Way, if you go really close to the center, there's so many stars, so many cataclysmic events like supernovae, there's a lot of radiation that it wouldn't be very hospitable to life. And if you go far enough away, then there hasn't been enough processing to make the metals that you would need to make planets like Earth, hard, rocky planets. So there's sort of even a habitable zone of our galaxy. Now, one of the cool things is if you look at our galaxy, the average age of the stars that would host potentially Earth-like planets is much older than us. It's, in fact, 2 billion years older than our star. So if the average age of Earth-like planets is 2 billion years older than ours, and life is easy to create, why haven't we seen it yet? Why hasn't it? You can imagine that given 2 billion years, we're going to get off this planet and go and visit a whole bunch of other planets and be able to, populate the galaxy. So if we're relatively young on the scene, why hasn't that other life from other planets come to us? That's something that we might want to discuss in the discussion session. I'm going to skip this because but this is probably, as a cosmologist, I don't publish on planets very often. This is probably my main, if only, contribution directly to this field, which is, does the rapid appearance of life on Earth suggest that life is common in the universe? And this was just asking that statistical question. Life appears to have appeared really quickly on Earth as soon as we had a solid surface that wasn't being bombarded. So is that something that's, if life happened easily here, maybe it could happen easily elsewhere. But maybe it didn't happen easily here. Maybe we were born on Mars and then it came here, and that explains why it appeared so quickly. Okay, and to finish off, the reason why these transiting planets are so exciting is that not only can we know that the planet is there, but we can actually detect its atmosphere. And this is one of the leading ways that we might be able to detect life on other planets in the next couple of decades. Now, because what happens is as this star passes between you and or as the planet passes between you and the host star, it blocks the light, but some of the light gets through the atmosphere. Some of the light will be transmitted through the atmosphere. And you're going to be able to see from the light that's absorbed by the atmosphere what kind of chemicals are in there. And amazingly, things like this have already been done. So here is some real data where what you're seeing is the light from both the sun and the planet put together, and then the secondary eclipse is when the planet passes behind the sun, and all that you're missing there is there's a little bit of light reflected from the planet, so you're missing that. But then you get the bigger transit when the planet blocks the light from the sun, and you get a bigger dip. So this is real data from what it looks like as the planet passes in front of its star. And you can see that you can actually measure the difference between these two things, and you can detect some of what the atmosphere of the planet is made of. And that's been done I guess you can also see the different layers of the atmosphere by looking at just as it passes just behind the planet. Some of the atmosphere will disappear before the others, and you can actually see even the layers of the atmosphere. So as I said, this has been done. I'm not going to go through this in detail, but some of the space-based telescopes following up these planet discoveries have discovered water vapour and methane and carbon dioxide in the atmospheres of planets around other stars. And we can even measure which direction the planets are spinning by what I was describing before, because one side disappears before the other. And we've even been able to measure things like temperature inversion, where there's a stratosphere and different layers of temperature in the extrasolar planets' atmospheres. It's absolutely crazy to think about what we're actually able to measure in these planets that are orbiting other stars. So I'll leave it at that and mention that the next step is this new mission called TESS, which is the Transiting Exoplanet Survey Satellite, and it's launching just in a couple of years, and it will be able to monitor a much wider field of view, see much brighter stars and things that we can really follow up with better telescopes afterwards, and really try and see whether we can see any indications of life on these other planets. Because if we see something like oxygen, we know it's possibly coming from life, because it needs to be an out-of-equilibrium system that makes oxygen, for example, in an atmosphere. So thanks very much.
And last but not least tonight, we're going to hear from someone who might one day be able to fulfill Tamara's dream of getting to Mars. And he is an engineer and chair of hypersonic propulsion, who is working to revolutionise high-speed transport through clean-burning, hydrogen-fuelled engines that could make space even easier to access in the future. Could you please welcome Professor Michael Smart?
So thanks very much. So tonight, when my slides come up, I'll just give a bit of a short status of where we are in terms of getting to Mars. So we've talked a bit about Mars tonight, but I'm the rocket scientist, so I'm interested and excited about how you get to Mars. And there's a real lot of activity on at the moment. I know when I was a young person, 2015, we would have expected to have been to Mars by now. But things have not much has happened over many years, but in the last 5 or so years, things are really getting going. So I just wanted to give a status on where things are tonight. Oop. So did you press the right button? Okay, so the first thing is, for those of you who don't know, how far away is Mars? And so I have a nice slide up there with the orbits of both the Earth and Mars. And the important thing to know is both the Earth's orbit and the Mars orbit are ellipses, and they're moving relative to each other. And at certain times, they become quite close, and so the radius of the Earth's orbit is about 150 million kilometres around the Sun, and the Mars is about 228,000 kilometres. But the interesting thing is that if you want to travel from the Earth to Mars, you don't take off when they're next to each other. What you do is you start way before the Earth, when the Earth is way behind Mars, and you take off ahead of the Earth and you catch up to Mars at a certain point. And what I've shown there is actually the standard, what did NASA call it? Their standard mission, where you could depart the Earth from January the 17th, 2014, and you would arrive at Mars in August, and then you'd stay on Mars for a long period, and then you'd leave and come back. So Mars is a long way away, and there are lots of important technological reasons why we haven't made the trip. And as I said, in terms of trying to get to Mars, things went through quite a long hiatus, but there's lots and lots of things going on now. I'll talk about Mars 1 in a moment, but there are all sorts of trips. There's the Mars 1 trip, which is doing things as cheap as you can and getting to Mars and staying there, and then there's your traditional NASA type mission, which will end up being an international mission. And so, if I describe the NASA one first, if you're going to go to Mars and survive, you're going to need a lot of kit. The probes that have been sent to Mars recently and the landers are really quite small, and they've used a lot of technologies which wouldn't be applicable to a much bigger situation where you want to land humans on Mars. So what you would do is you would, before you sent your astronauts off, you'd send a lot of kit ahead of you, so it was all there for you to use when you get there. Some of that kit would then land on Mars, and then the astronauts would follow them down. You'd stay on Mars for your period of time, approximately 500 days, as I indicated on the last slide, and then you'd fly back. So that's really the standard mission to Mars. Of course, the Mars 1 mission is to leave the second half there, right? So you go to Mars, you land, and that's your life. And who in the audience would be interested in doing that? There's lots of people who'd be interested in doing that. Sorry? Only if there's Wi-Fi, right. Well, that could be arranged, I think, yeah. There'd be an 8-minute delay, though, to get from Earth to Mars. Anyway, so that's how we could get there. But there are some really important technologies that need to be in place before that will happen. And the first and most difficult part, actually, is to get all that stuff from the Earth up into low Earth orbit. And NASA's method for doing that is to design actually the biggest rocket that's ever been designed. And they're in the process of doing this. The problem is that rocket is the biggest that's ever been designed, but they need between 5 and 7 of them to get all the stuff into orbit that they would need to take to Mars in order to get there and come back again. Okay, so it's a serious amount of kit, and there's really no getting around that. Earth is in what's called the gravity well, and getting to low Earth orbit, as people say, getting to low Earth orbit is halfway to everywhere in the solar system particularly. So that's the first difficult thing, but that's about grunt. We know how to do that. It's just about money, and it's about designing a big rocket. The next thing is, how do you get from low Earth orbit to Mars? What propulsion system do you need? Now, there are all sorts of modern concepts. There's the classic chemical rockets, but they're really not that efficient. There's lots of other more advanced propulsion systems that have been worked on, and they tend to be lower in thrust, but very efficient. So you tend to need quite a large vehicle. If you want to get to Mars, from Earth to Mars quickly, you basically need a very big vehicle, so you can have a very large, high-efficiency engine. And there are some concepts that you see around the place. So, we think we have that technology in place. Then, of course, there's keeping astronauts alive. There are 3 bad things about travelling for 500 days in space. One is the radiation, which I've indicated here. So the Earth's magnetic field protects us from a lot of solar radiation. A large ship could have its own magnetic field. That's a possibility to protect all the astronauts. So that's one dangerous thing. The second dangerous thing is the lack of gravity. Our bodies are made to be in a gravitational field, and if they're taken out of that, there are some severe medical issues. And the third one is just being locked up in a can with 5 other people for 500 days. And really, that's probably the biggest problem. The others are scientific, technical problems. That's a psychological problem and a human condition problem. But all these things can be sorted out. But there are some major things that need to be done for the trip over. Now, from an engineering perspective, the hardest part that hasn't been solved is, how do you land? there are different ideas that have been used for these rovers, but they're just not applicable to men. If you remember, one of the rovers was basically dropped inside a whole lot of big rubber balls and bounced along the Martian surface like 10 or 20 times. I don't think any of the astronauts want to be inside a big one of those. I know I certainly wouldn't. But we really don't even know how to do this. We see this in movies where the rocket just comes down and lands, but as an engineer, the amount of propellant you need to slow yourself down with a rocket is an enormous amount of propellant. And propellant is mass which could be used for other things. So from a rocket scientist's perspective, this is the thing that we don't know how to do. What we'd really like to do is somehow use the atmosphere that's around Mars and use that to help us slow down. But it's really not very thick, especially compared to the Earth. And so we don't have concepts yet for doing this. So this is really the biggest problem that we have. Cool. And then, of course, getting astronauts home. And the current thinking for that is that there's a lot of resources on Mars and you'll be able to make your own fuel there and use that fuel to take off and then come home. But of course, Mars One, the group there, they don't have that problem. They're going to Mars to start a colony and to continue essentially the exploration of the human race. So they have one less issue to deal with. So that's sort of a very, very quick summary of a lot of the technical issues associated with getting to Mars. They're all manageable, but as I say, the really difficult one that we haven't really solved yet is how do we land on Mars safely? So, thanks.
Okay, thank you very much. So I might invite the speakers to come and take a seat on these lovely couches we have here. And if you have questions at this point, if you could write them down, wave them in the air, and we will come round and collect those. I have one question here off Twitter already, but lovely. Okay, so Gordon, got the first question from you here from Steve on Twitter, who asks, how would the bacteria survive through space with no food source and the time spent in space?
Okay, good question. So one of the ways that we store bacteria in our laboratories here is by freezing them. So we'll have freezers not just like the -20 that you're used to using, but -80 degrees C. So the colder you can freeze bacteria, the better they'll travel. So if you think of space as being very cold, as long as you can make vitreous ice, you want amorphous ice crystals are bad for freezing life forms. They tend to pop them open. As long as you can freeze them quickly, then bacteria should travel. One of the interesting studies that was done, probably 20 years ago now, was microbiologists were isolating bacteria from inside insects that was trapped inside amber. And these things were millions of years old. And the bacteria cultured out of these insects just fine. So I would think that they could culture out of meteorites just fine as well.
Great. We have a question from Alison, who is 10. And I'll put this to the panel, and you can, whoever knows best. If Mars is the red planet, why is it not red to me? I guess why does it not appear red? I guess some of those pictures, it maybe is a little bit more vague on that bright red that we sometimes think of.
It can have depends. When it's very bright, like it was in 2003, that very close approach, and as I said, not all oppositions are the same, but it was marginally closer than other oppositions. You could distinctly see the colour, the reddish-orange colour. Our eyes aren't very good at seeing colour when things aren't bright, so when you look at the stars, a lot of them you don't really perceive the colour very well, although you do in some, like Betelgeuse or Betelgeuse. You can see that reddish colour, or Antares. But in Mars, so when it's fainter, the colour, I must admit, does get a little bit more subtle than when it's bright. So, but it is the red planet. It's certainly the red planet, and that certainly captured the attention of people in ancient times, named, as I said, for the Roman god of war.
Great. I'm not sure if this is a question for Gordon or someone else, but the question is, what is underground on Mars?
Well,
feel free to take your time.
Yeah. So we define the deep subsurface on Earth as anything less than 50 meters below Earth's surface. From a quarantine perspective in Australia, it's anything below 2 meters, right? Is differentiating the soil or the surface environment from the subsurface environment. The challenge in Mars is that we're trying to drill down into rock using basically the power that you would need to run a 7-watt light bulb, right? Very different than what we can do on Earth. In the gold mines in South Africa, we drill down 4 kilometers, all right? So until we can get a lot of energy or a lot of power onto the surface of Mars, it's going to be hard to get at that deep subsurface condition.
But the not so deep subsurface conditions, I think one of the big news stories that was alluded to recently was the water emerging from just under the surface. So it looks like there's a water on Mars now that's just hidden under the surface, so it's just sort of frozen. That can get the streams that they were seeing were seasonal. They came and went with depending on the temperature on the surface, and so it looks like there's the liquid water. That was what they looked with spectrographs from a space telescope, and could tell that this was liquid water emerging just at the present day, which was the exciting recent result as well.
Speaking about the underground, just going back to that colour of Mars, that reddish colour is only surface deep, really. If you dug down, it's not oxidised, it's not rusted. So just linking the two questions.
The other view there in terms of the subsurface is the meteorite impacts, right? That if you blast a hole in the ground, you can see the layers that are there. So an easier way to sample the subsurface.
Okay. Question for Michael. In terms of landing on Mars, have they considered a type of parachute system, or is the atmosphere too thin?
Yeah, so for a small vehicle, a big parachute can work quite well. But if you're trying to land all the gear that you would need for humans, you're talking about landing, a large house, essentially. And it's just, because of the thinness of the Martian atmosphere, the size of parachute you would need would be enormous. So people are thinking about things, like aircraft almost, where you could deploy some wings and not slow down so quickly, but fly around a bit on your way down, and then look for a runway somewhere.
As Michael said, no one wants to ride bouncing balloons across for a kilometre or so across the surface, and you might think back to Curiosity, which on the Earth weighed 900 kilograms, the biggest rover sent to another world, and that was that 7 minutes of terror. You might remember the NASA video and watching the team there at Jet Propulsion Lab, and that was using aerodynamic braking, first of all. Had to get rid of that velocity. You used parachutes, you used the sky crane, which used rocket propulsion, brought it down, and then released Curiosity for the last little bit there, and then the crane flew away. And it is a problem trying to land and get back off. That's why some of the first missions that they are proposing for humans to go there don't land. You go there and use one of Mars's moons, Phobos, as your base, and you send robotic craft down and you operate them from the surface. And you have a time lag from Earth to Mars, whereas you don't have much of a time lag just from Phobos to the surface. So we may indeed not see humans land straight away when they go there.
It'd be a shame to go all the way to Phobos and not land.
And Elon Musk of SpaceX and the other ones, and Tesla and everything, he has said that he'd like to spend his final days. He wants to die on Mars. He just stresses he doesn't want to die on impact.
I guess they did do that when they went to the moon as well, right? The first missions orbited the moon but never landed. So
that's right.
Yeah, bit by bit.
Okay, we've got a few questions around life in the solar system and life in the galaxy. So kind of join these together, but take them bit by bit. First of all, is Mars the most likely candidate for life in the solar system? And perhaps related to that is, why do we think that we'd need liquid water to get for life on exoplanets?
Sure. So Is Mars the best planet in the solar system for life? I'd say we'll give it a second place next to us. The importance of liquid water is to catalyze chemical reactions, right? We have to dissolve things and take things apart and build things together. And we typically use water in a lot of our biochemistry. That it helps. It's a solvent that promotes reactions. In terms of living cells, we use membranes to isolate the inside of the cell from the outside of the cell, both in a liquid water realm. So, there's lots of interesting kind of ideas on could there be other solvents, things like methane at cold temperatures or ethane. But water is a special molecule, right? Just its ability to stay liquid over a broad range of temperatures. The idea that if you have a planet like ours that can be cold, coming from Canada, ice will float and insulate the rest of life from this cold environment. So there's a number of properties that make water the best solvent candidate for life.
And also, when we're talking about life, we can also talk about life like us, so carbon-based life, which, after all, is one of the easiest to make cool molecules out of. It's very, you can make all sorts of chains and all the hydrocarbons and proteins and things, carbon is a really, really handy molecule to be able to, or element to be able to work with for that. We could imagine maybe not needing liquid water to make life out of some other chemicals, but it's a bit more difficult to get the kind of complexity that you need to make life that would be interesting to talk to out of some of those chemicals.
And don't restrict yourself to planets either. Everyone's upset, not everyone, but a lot of people are upset that Pluto was demoted to dwarf planet, but it's turned out to be one of the most fascinating objects in our solar system, and there's more to come. But there's moons of Jupiter, Europa, for example, tidally stressed, heated, which we think has a subterranean ocean under its crust, maybe as much as 100 kilometres deep in that ocean, more water than on planet Earth. So there are other locales in our solar system alone, not counting what has been referred to with the exoplanets and other locations. So often I say to people, it's daunting either way. Is this the only place in the universe where there's life? That's pretty daunting. Or is the universe teeming when you think that we've got our solar system, we've got a Milky Way with hundreds of thousands of millions of stars, and we think there are more planets than that, not all Earth-like. And then you've got now even, we used to say there are more galaxies than there are, more stars than there are grains of sand on all the beaches of Earth, and that's an underestimate, we think, now. So is the universe really teeming with life? And from another point of view, I think there's probably life already on Mars. We'd probably put it there because NASA has a sole position of planetary quarantine officer. And when missions go to Mars and landing missions, they're meant to be sterilised to the best you can do. It's not good for electronics sometimes. The Vikings were certainly baked quite a bit. But can we be sure that the Soviet Union, with theirs in the early 70s, Mars 3, actually landed, but might have got toppled over in a global dust storm at the time and stopped transmitting seconds after landing? Was it really sterilised sufficiently? Could bacteria have carried along in the warmer parts of that spacecraft and have got there? So we might have already put life there.
All right, you got energy for a couple more questions? We're moving international now. I've got questions about how many countries are involved in the effort of travelling to Mars? This is from Christopher on Twitter.
So the United States, obviously, the United States government, but there are private companies or private groupings within the United States who are interested as well, so it's not just governments. But I think China is interested in going to Mars. Other smaller countries, Japan has a mature space industry. India just sent a probe to Mars on their first attempt, actually. They did an amazing job. So space exploration, going to Mars, learning about it is really very international nowadays. And I think most people expect that the first real mission to Mars will be an international collaboration. It won't just be one country that does it. And it may be a company, but probably not.
And there is the European Space Agency, which is
Thank you.
a whole lot of European countries as well.
So just touching on that, Michael, we've been asked for your thoughts on SpaceX and the related private companies. You know, how do you see those private organisations playing a role in the future? You know, is that where we're going, or is NASA and the ESOA, is that where we should be?
I think SpaceX may not be the ones that actually go, but just the fact that they're there pushing the envelope has really had an effect on how NASA behaves, and how these government agencies behave. It's really been a breath of fresh air that's come to the space agencies and just space in general, is to have these very, essentially extremely wealthy individuals who are not trying to make money. They're just something that they want to do, and you know, rather than buying another Ferrari or whatever, they decide they want to go to Mars. And it's actually been a great thing for technology. I think a lot of new ideas are taken on by these groupings, which wouldn't perhaps get through the conservative barriers that are in these government agencies. So I see SpaceX and others as a real boon for the space industry and space exploration in general.
SpaceX is actually going to launch TESS, that planet-finding telescope that I talked to you about. They've got the contract to do that.
Right.
I might mention some of the Apollo astronauts, those are still alive, we've lost some, bemoan the fact that, like Gene Cernan, who was the last person to walk on the moon in December of '72, bemoans the fact that he's still called the last person to walk on the moon. And they really appeal to the young ones, and we've got young ones in the audience tonight, that you know, they dream about getting to other destinations, even if it's returning to the moon, which we haven't finished with, although Obama thought we had, and wanted to move straight to asteroids or Mars. But and some of the astronauts also feel like Walt Cunningham has talked about us being too risk averse these days compared to what they were in the 60s. They measured the risk, but they took it, like with the mission that was referred to, Apollo 8, which went to the moon at Christmas time of '68. The first humans to ride a Saturn V, and they sent them without any lunar module, no lifeboat mode like happened on Apollo 13. They took those risks, but they calculated them. But now NASA of today would never probably launch an Apollo 8 in the current environment. So we need to loosen up a little bit, measure things, but yes, and if it comes down to doing it and making money, that's probably the big thing. If there's a commercial return, we'll probably see those private companies go there.
Yeah, I think that's so true. I find it really frustrating, actually, that no one has walked on the moon in my lifetime. And I turned 40 the other day, so that's quite a long time. But and I think that's almost astonishing to think that it really has been that long, and that if we don't keep pressing forwards and taking an occasional risk, then sometimes it is possible to just go backwards.
I didn't want to retire from the planetarium until people had walked on the moon, and now it's slipping out of reach. But I say to kids, the first people to walk on Mars, hopefully, in school at the moment or in university at the moment, if you're looking at 20, 30-year time frame, there could be people in this room tonight that will, not talking Mars 1 or something, but, you know, coming back, that are here. So there's a challenge, and I sort of think people missed on a great age in the Apollo age. I used to skip school for the missions, you know, but you know, people should keep dreaming, and they can achieve their dreams.
Well, there you go, school students. Mark has put a deadline on you to get to Mars before he has to leave the planetarium. So I think that's a fantastic note to finish on. Ladies and gentlemen, could you please join me in thanking our fantastic panel tonight, Mark, Tamara, Gordon and Michael. Nuku has some very small gifts of thank you, and we'd love to join you all outside afterwards, and have a very Merry Christmas.